Hello again, I'm Rania Badry, Assistant Lecturer at Physics Department, Faculty of Human and Science University. Our second talk today will be about application of carboxymethyl cellulose sodium copper oxide nanocomposites as a sensor for NH3 and H2S gases modeling approach. This work under supervision of Professor Nadra Nada, Professor Mahmoud al-Nahas, and Professor Hanan Hayes. Our outlines are introduction, aim of the work, calculation details, building model molecules, results and discussion, and finally conclusion. Recently, the detection of toxic gases has been categorized through highly explored detection techniques. Among them, molecular modeling, which is one of the most rapidly processing areas in science that can make a connection between experimental and theoretical work. Molecular modeling also covers several fields including computational chemistry, drug design, computational biology, nanostructures, and finally material science. Features of molecular modeling are accurate and safe, easy processing method. In addition to this, disadvantage of experimental work such as hazards of dealing with either explosive or harmful substances and consuming both time as well as cost are disappeared by the appearance of computational modeling. The major aim of this work is to understand the mechanism of surface interaction of CMC and to improve the surface reactivity of CMC by the interaction with copper oxide nanoparticles, and finally studying the sensitivity of CMC copper oxide surface to ammonia and hydrogen sulfide gases. Calculation details. CMC and CMC copper oxide nanocomposites were optimized using Gaussian 09 program at Spectroscopy Department, National Research Center. All computations were performed with DFT utilizing T3-lib method. LAN L2DZ base set was utilized because it's considered to show exact commons about with all periodic table atoms, especially transition metals. Building model molecule of CMC and CMC copper oxide. The first goal in this study is to understand the mechanism of surface interaction between CMC and copper oxide. Based on the literature, it's concluded that the interaction between polymers and different metal oxides will be processed throughout the functional groups of the polymer and the oxygen atom of the metal oxide. As we see that in the structure represents CMC, there are a number of functional groups of hydroxyl groups presented at the terminals and throughout the chain, and also the all linkage between the two units of CMC and also the carboxylic groups present in the structure. Also, to confirm this, the molecular electrostatic potential maps were also calculated for dimer CMC structure, as we see at the right figure, where the molecular electrostatic potential maps are described by color range starts from red to blue, whereas the red color represents the electron-rich regions, while the yellow regions refer to the neutral ones, and the blue color refers to the proton-rich region. Therefore, based on the obtained molecular electrostatic potential maps of dimer CMC, there are 8 active sites are found in the proposed dimer CMC structure. These active sites are the hydroxyl groups located at the terminals and at the middle of the CMC structure, and the T double bond group present in the top and bottom of the structure, and also the O linkage along the chain. Results and discussion. Total dipole moment and homolomo band gap energy are calculated at T3-lib LAN L2DZ level of theory for dimer CMC and dimer CMC copper oxide structures in both cases of interaction, conflict, and absorb. As we see from the two tables, that the two parameters are affected strongly by the interaction with copper oxide in both interaction mechanisms, and that the interaction proceeds through the hydroxyl group is the most probable one, as it has the highest total dipole moment and the lowest band gap energy. Also, molecular electrostatic potential were also calculated for CMC interacted with copper oxide throughout the hydroxyl group present at the terminal to confirm the total dipole moment and the homolomo band gap energy results. Also, we see that in comparison with the electrostatic potential of dimer CMC, we see that the intensity of the red color increased around the structure for both cases, complex and absorbed interaction. And additionally, there is no differences between the molecular electrostatic potential of dimer CMC copper oxide structure in both cases of interaction. Sensitivity of dimer CMC copper oxide surface to NH3 and H2S gases. The following figure shows the model molecules optimized for NH3 gas and H2S gas and for CMC copper oxide interacted with the two different gases. This table shows the total dipole moment and HOMO-LUMO band gap energy values for the two different gases and the proposed structure of dimer CMC copper oxide interacted with the two gases. And we see that both physical quantity undergoes a strong change in their values upon the exposure to NH3 and H2S gases, which indicates the sensitivity of the proposed structure of CMC copper oxide to these two different gases. The results showed that copper oxide improves the electronegativity of dimer CMC surface and that the interaction can be absorbed more than complex. Also, total dipole moment and band gap energy of dimer CMC copper oxide structure suffered strong changes due to the exposure to NH3 and H2S gases. So that we can conclude that dimer CMC copper oxide structure can be used as a sensor for NH3 and H2S gases. Thank you for your attention.